The Embraer 190 has a retractable tricycle landing gear system with 2 main landing gear assemblies and 1 nose landing gear assembly. The main landing gear assemblies are telescopic and retract sideways into the wing and fuselage. Each main landing gear assembly incorporates 2 wheels with multi-disc carbon brake assemblies. The nose landing gear assembly is telescopic and retracts forward into the fuselage. The nose landing gear assembly incorporates 2 wheels with a hydraulic nose wheel steering mechanism, allowing the aircraft to turn on a taxiway as narrow as 17 meters. During normal operation, the landing gear system is electronically controlled and hydraulically operated. Several proximity sensors are installed to provide position and status signals to different electronic modules, located in the Modular Avionics Units, or MAU, for control and monitoring purposes. The sensors also display system status to the pilots via the ICUS display in the cockpit. The following equipment is installed in the cockpit for landing gear extension and retraction. The landing gear lever, for extension and retraction of the landing gear during normal operation. An electrical override switch is used to extend the landing gear in case of a failure in the landing gear electronics. And an alternate gear extension lever used for free-fall extension of the landing gear in case of both electronic and hydraulic system fail. The cockpit equipment for steering the aircraft includes a steering hand wheel, the pilot's and co-pilot's rudder pedals, and disarming switches on the control yokes. 2 brake pedals for the left and right main landing gear brakes are installed for both pilots. An emergency parking brake handle mounted on the center pedestal allows for braking even in case of a total hydraulic system loss. An optional automatic braking system can be engaged by the crew by selecting the respective auto brake switch in the cockpit. The position and warning system incorporates 2 identical proximity sensor electronics modules, or PSEM. Various system proximity sensors, such as weight on wheel or landing gear up and downlock sensors, are connected to the PSEM. The PSEM controls the extension and retraction of the landing gear and indicates position of the landing gear system, the ground spoiler system, and the aircraft doors. The nose wheel steering control module, NWSCM, controls the towing lights. The towing lights provide a visual indication of whether towing is allowed. The PSEM also controls the air-ground system. Proximity sensors on the nose and main landing gear, referred to as weight-on-wheel sensors, sense whether the aircraft is on ground or in flight. Weight-on-wheel sensor status is distributed to various aircraft systems via the ASCB. The landing gear system of the aircraft uses Hydraulic System 1 and 2 to perform the various functions. Hydraulic System 3 is not used. Hydraulic System 1 provides hydraulic pressure for the following systems: main landing gear braking, outboard wheels; main landing gear braking, emergency parking outboard. Hydraulic System 2 connects to the following systems: main landing gear and nose landing gear extension and retraction; main landing gear braking, inboard wheels; main landing gear braking, emergency parking inboard; and the nose landing gear steering. The main landing gear assemblies are attached to the left and right wings. The assemblies include 2 wheels with brakes attached to a telescopic shock strut. A folding side stay holds the main landing gear in the fully extended position. A locking stay holds the side stay in the fully extended position. Proximity sensors transmit the following signals to the Proximity Sensor Electronic Module, PSEM. Main landing gear down and locked. Main landing gear up and locked. And aircraft on ground, also referred to as WOW, weight on wheels. During retraction, a hydraulic release actuator unlocks the locking stay. A hydraulic retraction actuator retracts the main landing gear. The up lock holds the main landing gear in the retracted position. There are 2 doors attached to the outboard side of each main landing gear. A third door is attached to the wing. The doors are mechanically opened during extension and closed during retraction. The nose landing gear assembly is attached to the forward fuselage. 2 wheels and a hydraulic steering motor are attached to a telescopic shock strut. A folding drag brace holds the nose landing gear in the fully extended position. A locking stay holds the drag brace in the fully extended position. A pair of downlock springs hold the locking stay in the extended and locked position. Proximity sensors and feedback sensors transmit the following signals to the proximity sensor electronics modules and the nose wheel steering control module. Nose landing gear down and locked. Nose landing gear up and locked. Aircraft on ground. Nose landing gear steering angle and nose landing gear steering over travel. During retraction, a hydraulic release actuator unlocks the locking stay. A hydraulic retraction actuator retracts the nose landing gear. The up lock holds the nose landing gear in the retracted position. 2 mechanically operated doors are mounted in the fuselage on each side. The forward doors close again as the nose landing gear reaches the extended position. There are 3 modes of landing gear operation available to the crew: normal extension and retraction, electrical override switch, and alternate gear extension lever. In the normal extension and retraction mode, the landing gear actuation is electronically controlled and hydraulically operated. The landing gear selector valve is controlled by the Proximity Sensor Electronic Module, PSEM. The landing gear selector valve provides hydraulic pressure to the actuation cylinders. In the electrical override mode, the landing gear extension is electrically controlled and hydraulically operated. The extension override switch takes direct control of the selector valve. Proximity Sensor Electronic Module is removed from the control loop. In the mechanical freefall or emergency extension mode, the landing gear extension is mechanically controlled and gravity-powered. Pulling the cockpit manual release lever mechanically releases all landing gear uplocks and activates the freefall selector valve. Gravity and aerodynamic forces will then extend the landing gear. During normal operation, the crew uses the landing gear control lever in the cockpit to select the landing gear up and down. The control lever system consists of a lever to command extension and retraction, a down release button, and an illumination panel. A locking solenoid prevents the pilot from selecting the control lever up position while the aircraft is on ground. The lever can be mechanically released using the down release button. The 4 main landing gear wheels are equipped with electronically controlled and hydraulically powered carbon composite brakes, brake wear indicators, and fusible plugs which melt and reduce tire pressure safely if there is a wheel overheat of between 691 and 749 degrees Celsius. The brake control system uses electronic modules, sensors, and hydraulic valves to control the aircraft brakes for normal braking mode, and it has an optional auto brake mode. 2 brake control modules, or BCM, and 1 optional auto brake control module, ABM, control the hydraulic pressure to the inboard and outboard brakes. With the auto brake switch in the cockpit selected on, the ABM will apply the brakes automatically after landing and following a rejected takeoff. The anti-skid control system prevents wheel skid when the brakes are applied. The emergency parking brake system allows brake operation even with a loss of hydraulic pressure. The brake control system consists of the following main components: 2 cockpit brake pedal assemblies, 1 optional auto brake switch, located in the cockpit, with 5 auto brake selections for various auto brake modes, 2 identical brake control modules, BCM1 controlling the outboard brakes and BCM2 controlling the inboard brakes, and 1 optional auto brake module, ABM, all located in the MAU. 2 brake shutoff valves supplying or isolating hydraulic pressure to the brakes depending on various conditions. 2 brake control valves, one for the inboard and outboard brakes to regulate the hydraulic pressure. 4 pressure transducers provide hydraulic pressure signals to the brake control module. 1 hubcap drive per wheel, incorporating the wheel speed transducer, which transmits wheel speed signals to the brake control module. The left and right pilot and co-pilot pedals control the left and right brakes independently during normal operation, allowing the pilots to steer the aircraft using differential braking. The brake pedal LVDTs transmit brake pedal position to the BCMs. The BCMs use closed-loop electronic control to calculate a pressure command for each main landing gear wheel brake, relative to the pedal position. The brake control modules add several high-level functions to optimize braking performance during various conditions. Anti-skid control reduces the pressure command to any wheel by comparing wheel speed signals from each wheel in order to prevent wheel skid on slippery runways. Anti-skid protection is active when wheel speed is above 10 knots. Touchdown protection inhibits a pressure command for any wheel if the aircraft is in flight, or when the aircraft is on ground for less than 3 seconds. However, a spin-up override function allows braking when wheel speed is above 50 knots, even when touchdown protection is still active. The brake control module may also reduce the pressure command for a wheel if the wheel speed of a pair of wheels, either an inboard or outboard pair, is above 30 knots and one wheel in the pair turns at less than 33% of its partner's speed, called locked wheel protection. After takeoff, the brake control module applies a pressure command to all wheels for 4 seconds, when weight on wheel signal indicates the aircraft is in flight. The landing gear selector is moved from down to up, and the proximity sensors indicate that the landing gear is not down and locked. The brake control modules also control the 2 brake shutoff valves in order to isolate the brake control valves from hydraulic pressure. In flight, the BCMs de-energize the brake shutoff valves, isolating hydraulic supply to the brake control valve 10 seconds after the aircraft has left the ground, when the landing gear selector is in the up position and wheel speed is 0. The brake system is depressurized during flight. Before landing, when the landing gear selector is moved to the down position, the shutoff valves are energized again in order to perform a brake control valve test sequence, including a change in the brake pressure command by 600 psi, which must be confirmed by the pressure transducers. Following a successful test sequence, the shutoff valves are de-energized again before touchdown and remain de-energized as long as touchdown protection is active. The auto brake module provides pressure commands to the brake control modules if the auto brake control is active. Auto brake control can be selected on or off by the crew by means of the auto brake selector switch in the cockpit. The following auto brake modes can be selected: RTO for automatic braking following a rejected takeoff, low, medium, or high for 3 different levels of deceleration after landing. During landing auto brake application, the deceleration rate is calculated by the ABM using changes in ground speed. The crew can reselect the deceleration to any of the 3 levels without disarming the auto brake. If the brake control system detects a fault, the auto brake selector switch springs back to the off position. The following BCM protections are still available during auto brake control: anti-skid control, touchdown protection, and locked wheel protection. Landing auto brake control can be armed by the crew under the following conditions. The auto brake selector switch is set to low, medium, or high. Left and right weight on wheels indicates that the aircraft is in flight. The average wheel speed is below 60 knots. Brake pedals are not pressed in. And no brake control system failures are detected. Landing auto brake control will be applied after touchdown when the following conditions apply. Landing auto brake is armed and the average wheel speed is above 60 knots. Either weight on wheels indicates aircraft on ground for more than 2 seconds. And both thrust levers are in idle position. Landing auto brake will be disarmed if the selector switch is set to off, the brake pedals are pressed in, any failure in the brake control system is detected, or either thrust levers advanced beyond idle. Rejected takeoff auto brake can be armed by the crew under the following conditions. The auto brake selector switch is set to RTO. The left and right weight on wheels indicates that the aircraft is on ground. The average wheel speed is below 60 knots. And no brake control system failures are detected. RTO auto brake control will be applied during a rejected takeoff if RTO auto brake is armed and the average wheel speed is above 60 knots, and both thrust levers are in idle position. RTO auto brake will be disarmed if the selector switch is set to off, any braking is applied while wheel speed is above 60 knots, any brake control system failure is detected while wheel speed is below 60 knots, or either thrust lever is advanced beyond idle. The emergency parking brake system is mechanically actuated by means of a handle located on the center pedestal in the cockpit. The handle can be moved 60 degrees between the stowed and full brake position to regulate the emergency brake. The handle locks at 60 degrees to set the parking brake, and the emergency park brake on light in the cockpit will illuminate. One side of the valve is connected to hydraulic system 1 and actuates the outboard brakes. The other side is connected to hydraulic system 2 and actuates the inboard brakes. The system is isolated from the normal hydraulic supplies by check valves. In the event of a total hydraulic failure, emergency braking is still available to both inboard and outboard wheels through the emergency parking brake valve, using hydraulic pressure from the accumulators. Shuttle valves allow either normal or emergency brake pressure to activate the brakes. The MFD status page has 2 ways of providing temperature indication: numerical and pictorial. There are 2 brake temperature categories on the MFD. Temperature indication is green, up to 251 degrees Celsius, which means that the brakes are able to absorb maximum kinetic energy. Advisory indication is shown in amber between 252 degrees and 840 degrees Celsius, which indicates that cooling is required. If the temperature information has failed or is out of range, the arrow will disappear, and the readout will be replaced by amber dashes. The brake overheat caution message will illuminate on the ICUS when the brake temperature has exceeded the normal operating range. The message will disappear if the temperature drops below a predetermined value. If the brake temperature reaches 750 degrees Celsius, the advisory message, "Landing gear temperature exceedance," will latch and can only be unlatched by electrically powering down the airplane. Note that the fuse plugs will melt in the main wheel, and inspections, according to the maintenance manual, have to be performed. The Embraer steering control system is an electronically controlled and hydraulically actuated steer-by-wire system, operating either in the normal mode or in the freewheel steering mode. The system consists of the following main components. The steering handwheel, located on the left side in the cockpit, used for low-speed steering control. The pilot's and co-pilot's rudder pedals, used for high-speed steering control. And the disarming switches, located on the cockpit control yokes and on the left forward fuselage, used for switching between normal and bypass mode, allowing towing. The nose wheel steering control module, or NWSCM, electronically controls the steering hydraulic system. The steering control system is powered by Hydraulic System 2. The steering handwheel is attached to the left side of the cockpit. It incorporates a switch and a rotary variable displacement transducer. To turn the aircraft, keep the handwheel pushed down and rotate it. The RVDTs transmit the position of the handwheel to the NWSCM. The maximum steering angle possible using the handwheel is 76 degrees and is limited further by the NWSCM as aircraft wheel speed increases. At taxi speeds from 40 to 100 knots, the steering angle will be gradually reduced down to 7 degrees. Steering angle response to handwheel position is non-linear. Turning the handwheel from 0 to 40 degrees results in a steering angle of 10 degrees, and from 40 to 80 degrees results in a steering angle of up to 76 degrees. The system can be operated either in the active mode, once the handwheel has been pushed down, or in the freewheel steering mode. In the active mode, the flight crew actively steers the aircraft by means of the handwheel rotation, keeping it pressed in down position, or by the rudder pedals if the nose landing gear is on the ground and the NWSCM detects no failure. In the freewheel steering mode, the nose landing gear steers in response to external forces like towing or differential braking, and is enabled as soon as the steering has been disengaged using the pilot disarm switch or via the outside steering switch to disengage position for ground handling. Steer off will be displayed on the ICUS. The freewheel steering mode is also automatically engaged anytime the actual steering angle is greater than 76 degrees. If the crew switches from the freewheel steering mode to the normal mode, the steering command from the NWSCM is gradually changed from the actual steering angle to the handwheel or rudder pedal command angle. Two channels control and monitor the steering system. The nose wheel steering control module compares the difference between rudder pedals or handwheel position and the actual nose landing gear steering angle received from the steering angle feedback sensors. Nose wheel steering control module commands the electro-hydraulic servo valve, EHSV, on the steering manifold to cancel the difference, resulting in a nose landing gear steering movement to the requested position. After takeoff, nose wheel steering control module switched off, and the nose wheel will be centered by the internal centering mechanism when the shock strut extends. The nose wheel steering control module controls the two towing lights installed on the nose landing gear strut. A green light signals the ground crew that towing is permitted, and a red light signals that towing is not permitted. Towing is not allowed when the steering motor is pressurized, operating in active mode, or if any of the brakes are pressurized. Whenever a safety-critical failure is detected by the nose wheel steering control module, the nose wheel steering is switched to the free caster mode. On the ICUS, a steer fail caution is displayed when the landing gear is down. After this system disengagement, the nose wheel follows freely in the direction of ground run, and steering can be carried out by use of differential braking and/or by rudder commands. A steer fault advisory message will be displayed on the ICUS in the case of a degraded function of the steering system after a failure has been detected by the nose wheel steering control module and the aircraft is on the ground. The status message, "Steer off," will be displayed if the steering system is disconnected, for example with the steering disarming switches. An LG No Dispatch caution appears in case of a nose wheel steering over travel, proximity sensor evaluation module, PSEM, or weight on wheel system fault. The landing gear position and warning system is used to provide landing gear status and failure information. The system has the following subsystems: the landing gear indicating system, the air ground or weight on wheel system, and the landing gear warning system. The landing gear indicating system is controlled by two identical proximity sensor electronics modules called PSEM, installed in MAU-1 and MAU-3. The PSEMs each make an analysis of the proximity sensors for the landing gear system, ground spoiler system, and aircraft doors. The air-ground system makes use of proximity sensors on the main landing gear and nose landing gear to determine whether the aircraft is on the ground or in flight. The landing gear warning system forwards failure information to the ICUS and warns the pilots of any abnormal landing gear configuration during landing. The ICUS indicates the landing gear position using three colored symbols. From left to right, each box represents the position of the left, nose, and right landing gear. With the landing gear down and locked, green circles enclosing a green word, "down," are indicated. If the control lever is moved and the gears are in transition, amber crosshatches are shown. If the landing gear is up and locked, white squares enclosing a white word, "up," are displayed. A disagreement between the control lever position and any landing gear leg position for more than 20 seconds will activate the message, "Landing gear lever disagree," and the indication of the respective landing gear will turn red. If at least one of the nose landing gear doors fails to close following gear retraction, or one of the two forward doors fails to close after If the RO landing gear warning is triggered as a result of an invalid radio altimeter signal, the pilots may cancel the warning by pressing the landing gear warning inhibition switch in the cockpit. When pressed, a white bar within the switch indicates a canceled warning. Advancing the thrust levers above TLA 38 degrees or TLA 57 degrees respectively, or selecting the flaps to landing configuration, or when all landing gear are down and locked, will extinguish the white indication.